Okay, I think we finished up 15 last time, which is good because exam is on Thursday, right, through 15. So we're going to move on, obviously, here to, I guess it would be exam 3 stuff. So we're going to go backwards. We're going to cover energy because here at the school, they don't do it in 200A anymore. So we're going to go back in the book, and then we'll come forward in the book, and we'll finish talking about sort of thermodynamics and stuff like that. So let's talk a little bit about energy here in this chapter. So when we talk about energy, a lot of times what we're dealing with, and a lot of times in thermodynamics, which is sort of what we are dealing with here, is really the idea of energy flowing from really one place to the next. And there's really kind of two things we think about in sort of thermodynamics and energy, which is the system. The system is pretty much anything that we are interested in. So, for example, when you do an experiment, obviously your system is like your beaker, maybe your test tube, whatever you may be doing. And then pretty much everything outside of that is considered the surroundings. And in terms of energy, it's usually one of two things occurring. Either it is kind of flowing from the system to the surroundings, or pretty much vice versa from the surroundings back into the system. One of the things, as we'll talk about here, and as you may know, is the conservation of energy, right? So we don't lose or create energy along the way, but it is, again, sort of transferred from one place to next. When we talk about systems, there's really, three types of systems that we kind of commonly come across. One's an open system, and that's kind of like your test tube, if you will. An open system allows both mass exchange and energy exchange with the surroundings. So like it's open, you get in there, dig stuff out if you want, and you obviously can allow the heat to move in and out. A closed system is kind of like if you take your test tube and like put a stopper on the top of it. That prevents obviously the mass from sort of leaving the test tube, but it still allows the test tube to exchange heat and energy with the surroundings. The last one, sort of an isolated system where we really do not transfer any mass or energy. In an isolated system, can't really remove what's in there. And then also is sort of insulated. So the outside surroundings is really not affecting, obviously, the temperature that's sort of inside. So that's more of an isolated type system. And here's sort of a picture of all three of those sort of systems. Again, in the first one, we could obviously exchange mass in and out, and obviously heat can go in and out. Again, if you stick like a stopper in there, that's going to prevent obviously you losing anything that's inside. It cannot escape, but we can still have the transfer of heat and energy. And again, in that isolated system, we're really kind of keeping everything within that particular system. So let's talk a little bit about energy and some of the different types of energy that we come across. Energy is really the capacity to do work or to produce change. We could use energy to do some type of work, or work can be done on something as a result of energy. There are chemical energy. Chemical energy is basically the energy that's stored within the units of chemical substances, like, for example, chemical bonds. So when we make a bond, say these two guys are going to come together to make a bond, we have to actually lose energy. So energy has to be given off in that process when you want to make a bond. So if you think about it, you got the sort of two bonds, they're moving around, they're vibrating. As they lose energy, they sort of slow down, and they're able to basically come together basically to make a bond. As opposed to if you actually had a bond and you wanted to break it, that requires energy basically being put in. So if you have a bond and you put energy in, everybody gains enough energy and they're able to sort of wiggle away from each other. That's exactly how it doesn't happen, but they wiggle away from each other and you will be able to break those bonds. A thing that we'll see sort of over in terms of energy is really two kind of popular words that basically represent both of these things, and that is a exothermic process. Exothermic means that basically heat and energy, our energy is given off or released. And that is different than endothermic. In an endothermic process, heat and energy is absorbed. So those are two really kind of key words in terms of energy to sort of describe what's going on in terms of energy and heat in a process. Other types of energy is potential energy. Potential energy is stored energy. The classic example, right, is the giant boulder on top of the hill has a certain amount of potential energy, and it's basically stored energy. Energy obviously can be transformed to one way or another. So you got the big boulder on the hill that then starts to go over the hill. And as it goes over the hill, that potential energy is turned into kinetic energy, which is the energy basically of motion. And then it splatters on the ground and it transfers its energy to the ground and rests at a new potential energy. So the idea of the law of conservation of energy is pretty that, and it's an important concept in terms of sort of reactions and things like that. The basic idea is pretty much simple. If somebody loses a certain amount of energy, there has to be somebody that will pretty much gain that same amount of energy. So there's sort of an equal transfer of energy. We sort of think about it that way. And again, we sort of think about system and surroundings. So if the system releases a certain amount of energy, the surroundings is there to pick up all that energy, and vice versa. Obviously, if the surroundings gives away all that heat and energy, there's some type of system there that will pick up that heat and energy. And again, we don't lose nor create any of that energy in a process. Any questions on that? So thermodynamics is the study of the interconversion of heat and other kinds of energy. And especially in this chapter, we're going to really focus in on energy. Later on, when we go back to the regular chapters here, like 17 or whatever number it is there, 16, we will talk about the rest of sort of thermodynamic properties. But the overwhelmingly sort of thing that we look at when we think about thermodynamics is usually whether or not the process will be spontaneous or non-spontaneous in this reaction. And when we think about spontaneous or non-spontaneous, it basically means that the reaction will take place under those conditions. It doesn't mean that the reaction will occur really fast or really slow. It just means under those particular conditions, we would expect the reaction to take place. When we talk about fast or slow, we're talking about really kinetics in that sense. State functions are properties that are determined by the state of the system, regardless of whether or not the condition was achieved or how the condition was achieved. So when we talk about state functions, it basically are things like energy, pressure, volume, temperature. It's basically final and initial. So where you start and when you end. And those are things like the change in energy is final minus initial, pressure final minus initial, volume final minus initial, and temperature final minus initial. So here, when we look at our two hikers in terms of potential energy, our blue hiker took the more direct route to the top, while our kind of red hiker took the scenic route there to the top. Regardless of their path, basically they both possess the same potential energy at this point. They both basically started in the same position, ended in the same position, and that is what a state function is. The only two really important things, where you start and where you end in terms of, That's important. And it has an importance in terms of reactions, as we'll talk about later, that you could do a reaction in 5 steps. You could do a reaction in 2 steps. You could do a reaction in 1 step. The overall energy to do those steps basically is the sum of all those steps, but it's basically your final minus your initial in this particular case. So there are some important units of energy, and some really important units of energy along the way are things like joules. Joules, which are a very common unit of energy. Kilojoules is also used a lot. Kilojoules is 1,000 joules. There is a nice relationship between a joule and a kilogram meter squared second squared. And that's a good relationship to remember. That does come about a lot, that a joule is a kilogram meter squared second squared. Perhaps if you remember, you learned root mean square velocity there. When you were talking about gases, that relationship popped up in there. Other kind of common units of energy are calories. A calorie is equal to 4.184 joules. None of these are negative. It's just all basically from PowerPoint there. Now, calorie is basically the energy that's required to raise the temperature of 1 gram of water by 1 degree Celsius. Now, there are 2 types of calories we sometimes come across. This is really the one that we use a lot when we're talking about energy. And this is really a calorie with a lowercase c, not to be confused with a capital C calorie. That is a nutritional calorie. And basically one of the big C for dramatic purposes there is actually equal to 1,000 of the little calories. And that is the same as a kilocalorie, which is another very common unit of energy that we come across. So calories, little calories, joules, kilojoules, and kilocalories are 3 really common units of energy that we use a lot. I would say for the most part, though, joules and kilojoules are probably the winner in terms of chemistry, in terms of the units that we use the most. One way that we use energy is to change the temperature of a substance. Obviously, a reflection of somebody gaining a lot of energy is that the temperature will start to increase, as opposed to obviously if somebody is losing a lot of energy, we will typically see obviously the temperature come down. If we take ice to liquid water, obviously that is an endothermic process. We need to put heat and energy into our ice, right? It's going to pick up all that heat and energy really from the surroundings. It's going to start to melt, and obviously we would get liquid water. We could reverse that process by taking the liquid water, right, throwing it into the freezer. The result of that is, even though we think about it as freezing it, what's really happening is it's like basically losing energy and becoming exothermic. So that water is now going to release all that energy to the surroundings of the refrigerator or the freezer. The result of that is all the water molecules are going to come back together and basically reform the ice. So when we talk about sort of changes of state, as you probably well know, hopefully as you go from solid to liquid to gas, those are all endothermic processes. You got to put heat and energy to do that. And as you go the opposite way, gas back to liquid to solid, those are all exothermic processes. Heat and energy needs to be released as that is happening. So if you just think about gas molecules flying around, when they release energy, they no longer are flying around as fast, which means when they collide with each other, they can no longer escape one another. So they will have to sort of drop out of the air and back into the solution. You continue to remove that energy, they're going to kind of cluster back together more into the solid state as well. Any questions on that? Now, thermal energy is the energy is really associated with the random motion of atoms and molecules. It is actually based on the amount of molecules that are present. The more molecules or atoms that are present, there's more vibrations. More vibrations means there's actually more thermal energy. And there is really a difference between sort of thermal energy and temperature. Again, temperature is sort of a reflection of the energy that's happening in that particular space. Thermal energy, again, is sort of based on, how much molecules or atoms there are and how much they are moving around in a particular location. Obviously, the more atoms moving around in a sample, or the more vigorously that they're moving around, they're going to generate a lot more energy and a lot more thermal energy. Now, the distinction between those two, for example, is if you take, for example, a cup of coffee that's 70 degrees Celsius, and it's a higher temperature than you say if you have a bathtub of warm water at 40 degrees Celsius. But in terms of thermal energy, there is a lot more thermal energy in the bathtub, as there's definitely a lot more molecules of water most likely in your bathtub than there is in your cup of coffee. So even though the cup of coffee has a higher temperature, the actual bathtub would have more thermal energy. The reflection of the higher temperature in the cup of coffee is also because it's a much smaller area, right? So you got all those guys in a much smaller area, can cause perhaps a bigger temperature change than all that water that you have, right, to get the temperature up. One of the things we'll talk about here in this chapter is specific heat capacity. Water has a very, very high specific heat capacity. It takes a lot of energy just to move the temperature 1 degree. So if you have a big bathtub full of water, it's going to take a lot of energy to really move the overall temperature of that, as opposed to a coffee cup, which is obviously a much smaller amount, doesn't take as much energy to see that bigger temperature change that occurs. Any questions on that? Yeah. It would be, yeah. So if you were magically able to kind of squeeze a bathtub into a cup of coffee, we know we don't get that much at Starbucks, right, when you order it. But yeah, it would technically, you would see a much larger energy change, or temperature change, I mean, in terms of that, because of that, yeah. Yeah. It would be, for example, if you had the same amount, like that was in the coffee cup, obviously, if you put it into that bathtub, it's obviously going to spread out, right? So, they're not going to be around each other that much in terms of motion. It's going to be much spread out, and they're actually going to probably lose a little bit of energy. So you would see the temperature come down. Yeah. Other questions? So heat is defined really as the flow of energy due to a temperature difference. And when we talk about heat flowing, does it flow from cold to hot or hot to cold? Heat and energy really does flow from the hotter guy to the colder guy. Yeah. So the hot guy kind of loses the energy to the cold guy, really. He picks up that energy. The colder guy will come up in temperature. The warmer guy will come down in temperature. And, if you're in a nice insulated container, maybe they meet somewhere halfway between their two temperatures. So if you think about if you took like a really hot piece of metal, which we'll do next week, I think, a whole bunch of pennies maybe we'll set on fire. And you take a piece of metal that's really, really hot and you dump it into a cup of water, right? Penny's temperature is going to drop, right? Water's temperature will go up because basically the penny will be, or the metal will be giving off that energy to the water. The water will be picking up that energy and we will see that rise that will occur. As we talked about earlier, really the two major processes that occur, exothermic, any process that really gives off heat and energy. For example, obviously, if you light a match, you can put your hand near it, or like a Bunsen burner or something like that. You could actually feel the heat and energy coming off of that to the surroundings. Endothermic process, one where heat is basically being absorbed. And you can even feel that too, if you do some type of reaction in a test tube, right? And you're holding the test tube. First off, if the test tube gets hot, that means that reaction is exothermic, right? Energy is being transferred from the test tube to your hand. Vice versa, if you're holding the test tube and do a reaction, it starts to feel really cold. it is a endothermic process because it is taking all the heat and energy from your hand to the test tube. Thus, your hand feels cold. The idea of like hot packs and cold packs, right? Where you kind of crack something and does like a chemical reaction, it gets hot or cold. And that's the idea behind that. Obviously, in a exothermic reaction, if you kind of crack the hot pad or whatever to do the reaction, it will be giving off that energy. And if it's on your hand or wherever you put the hot pack, it's going to be your hand that's going to basically absorb all that energy, and you will feel hot as a result of that. And vice versa, obviously, if you crack like a cold pack and did like one of those kind of chemical reactions, if it's endothermic, when you put it on your hand, it's going to basically draw all the heat and energy from your hand, and thus you will feel cold on your hand. Any questions on that there? These are energy diagrams, and one represents an exothermic reaction, one represents an endothermic reaction. And there's some important parts to these energy diagrams. First off, this is the energy of the reactants here. And this is the energy of the products. And just based on the location of those two in terms of the energy of the reactants to the products, that is basically what tells us this is a exothermic process. So whenever you see a energy diagram such as this, which has basically energy on the Y and sort of the progress of the reaction there on the X, that the energy of the reactants are higher than the products. Basically, the only way those reactants can get down in terms of the energy to the products is to give off that energy, and that would be an exothermic reaction. Again, the energy of our reactants higher than products. And we see the opposite here on the guy on the right. The energy of our reactants are actually lower in energy than our products, which means in order to kind of get up there, we got to put energy in to do that. Are absorbed. And that is obviously a endothermic reaction. So those are really two important spots on this energy diagram. The third really kind of important spot is actually the heel here. And at the heel, from where the reactants sort of start in energy to the peak of the heel, so that is that one right there, and over here, it is this one right here. That is what is known as the activation energy. So that is the activation energy, which is sometimes abbreviated E of A. The activation energy is the minimum amount of energy required for a chemical reaction to take place. So there's really two things that need to happen in order for a reaction to take place. And sometimes people think that basically all you need is the two things basically to come together and collide with each other, sometimes referred to as collision theory. And that is true. You do need them to come together and actually collide, but they have to collide actually in the right orientation. So the right things actually need to come together and sort of hit each other. The other thing that needs to happen is they need to have basically that minimum amount of energy for that collision to occur for products to form. There's lots of collisions that occur between reactants that don't result in products being formed because either it's not the right amount of energy or they hit in sort of the wrong orientation with each other. So those are two really important things that has to happen for a reaction to actually take place and for products to actually be formed. The other sort of consequence of the activation energy is it's sometimes referred to as sort of the hill that the reactants has to climb basically to get to the other side to make products. And when we think about the hills, it also affects how fast or slow a reaction will take place, right? So if you have a really giant hill that the reactants has to climb to get to the other side, it's probably going to take a little bit longer for that reaction to take place, as there's most likely a much smaller proportion of molecules that have enough energy to kind of go up and over the hill. As opposed to if you had a much smaller activation energy hill, there's probably a greater proportion of molecules that do have the sufficient amount of energy to kind of get up and over to the other side. The rate of that reaction will most likely be a lot faster. That's actually how catalyst works. They find an alternative pathway for a reaction to occur. The result of that is they lower the activation energy. By lowering the activation energy, there's now a lot greater amount of reactants that can get to the other side. And the overall result is typically that the rate of reaction will increase. Although not all catalysts increase the reaction, some actually slow it down. But most of the time, when people talk about catalysts, they talk about it in terms of it making the reaction occur a lot faster. Any questions on that? By the way, as this reaction is happening here, and as this guy is sort of progressing up the hill, for example, so as this guy is happening, what has to happen is essentially, as this guy is progressing up the hill, you're basically starting to break the bonds as we start to kind of head up that hill. In addition, what's happening as it goes up the hill is it's actually starting to make new bonds. That is the basis of chemical reactions. It is simply all we do is break all the bonds on the reactant side, and everybody kind of reassembles on the product side. When we get to the peak of the hill here, this spot right here at the peak of the hill is what is referred to, and I'll just draw it down this way. That is what is referred to as the transition state. And when you get to the top of the hill, you have something that is known sometimes as the transition state complex, or sometimes referred to as the activated complex. And what that thing is a guy that has kind of partially broken bonds. And some partially made bonds. So let's first talk about this guy that finds himself way up here at the top. In chemistry, things at very high energy, are they typically stable or unstable? Do things want to be at really high temperature? Do things really want to be at high energy in chemistry? No, pretty much everything that we do in chemistry is all about kind of reducing the overall energy basically that's happening. And what that means is our transition state complex are things that are very, very unstable. So typically what happens is once they kind of peak to the top, they kind of really quickly kind of drop down to the other side in both of these cases to the products being formed. That's why usually transition state complexes are usually very hard to isolate because they don't hang around a very long time because they're just sort of intermediate, if you will, between the making and the breaking of bonds as it comes down to the other side. Any questions on that? Now, something as we'll talk about in here, and we can kind of see on this graph after I've sort of scribbled all over the graph here. And just to clear it up real quick so we can see. If you take the energy difference between where the reactants start and where the products end in terms of energy, this is what is known as the heat of the reaction. As we'll see in just a second, it is also sometimes referred to as the delta H, and that is the enthalpy of a reaction. And the difference there would actually be a negative value if we take the difference in energy of our products, which is a smaller number than our reactants, which is a larger number. And this would be a negative number for an exothermic reaction. And that's opposite of what we see here. Our reactants and our endothermic is lower in energy than our products. So when we do our products minus reactants, which is our final state minus our initial state, we will end up with a positive value for the delta H, and that usually means it's an endothermic reaction. Any questions on that there? Now, between exothermic and endothermic, the one that has the larger activation energy is the endothermic, and that sort of makes sense. You kind of has to put energy in there. It needs to absorb some energy to help everybody up and over to the other side. So you typically do see sort of a larger activation energy in an endothermic reaction. Any questions on that there? And this is a different sort of energy diagram, but again, in our exothermic, the key here is this is our reactants. That's our products. Again, products lower in energy. That means heat and energy needs to be given off by the system, and we would expect this to be a exothermic reaction, as opposed to this is our reactants, and these guys are our products. And here, the products are higher in energy, so it would be absorbed some energy from the surroundings. So exothermic reactions are displayed a couple different ways. When we think of exothermic reactions, although maybe not perfectly correct, we do think of energy as like a product. So I think we talked a little bit about this in terms of Le Chatelier's principle. And you will sometimes see the energy sort of written in on the product side for an exothermic reaction, obviously 213 kilocalories. As opposed to an endothermic reaction, we sort of think of energy as a reactant in this case, and you will typically see the energy on the reactant side. I would say probably though in most cases in this type of class, you probably won't see it written into the equation. So there's really a few different ways that we can do that, and delta H is the most common way, as we just talked about. If that value is negative, it's going to be exothermic. It doesn't really matter the actual number, just the actual sign is important here. And if, again, as we just talked about, if our delta H is positive, it will be an endothermic reaction. Another kind of energy calculation that we sometimes do is Q, which is heat or energy. It's heat. And it works the same way. If you calculate Q and you get a negative number there, that's going to be exothermic. If you calculate Q and you get a positive number, it's going to be endothermic. So Q is a very common one that we sometimes calculate when we talk about specific heat. And again, positive is usually associated when we're talking about energy with a endothermic process, while a negative value for heat is important for a exothermic process. Now, sometimes in earlier classes, maybe they will teach you when you do something like specific heat to not worry about the positive or negative, but it is really important in terms of looking at a reaction and determining whether or not it's an exothermic process or an endothermic process. Yeah. You know, I will say never, but probably rarely. Yeah, I would say so. In this class, probably rarely, yeah. So you will be most likely, how an equation would be is you would be given this part of the reaction or the equation, and then next to it will be like a delta H value, and it'll either be positive or negative. And that's probably, I would say, 9 times out of 10 how you would see it. I would say maybe if you took like health majors, chemistry, they sometimes just kind of put the numbers into the equations. But it's still important to remember that, you know, again, not correct in all aspects, but we sort of think about exothermic as being sort of the energy on the product side, and then endothermic, the energy or heat being on the reactant side. Other questions? So again, as we talked about the energy here, if we had a nice isolated container, hot water on one side, cold water on the other, we would expect, again, basically that heat to be transferring over from the hot side to the cold side. And obviously, if I go the right way there, what we would see is, again, a lot more motion on this side, transferring that energy, going to allow these guys to really pick up some of that energy and also start moving a lot faster as well. And eventually what will happen in an isolated container like this is they'll meet somewhere in the middle of the two temperatures because it's nice isolated. Nothing's being lost to the surroundings or anything like that. You can do a very sort of good closed container or isolated container by just using like a simple coffee cups, basically. It's a nice insulated way, and you don't lose too much heat and energy to the surroundings in that, and that's what we'll use next week. Usually it's just coffee cup with a lid. So enthalpy, as I talked about a second ago, is really, how we display energy a lot in reactions. The enthalpy is sort of the overall energy change that occurs in a sort of chemical reaction. It is usually expressed as delta H, which basically means the change in enthalpy. And the one way that we could calculate the enthalpy for a reaction is basically because it's a state function, we could do products minus reactants. So if you remember, state function is basically where you end up and where you start. When you think about a chemical reaction, where you start is reactants, where you end up is products. So that is why we can calculate the delta H by simply actually going to a table. If you look in the back of the book, there is a delta H of F table. That's a delta H of formation table. And you basically would look up all the values for everybody on the product side and subtract it from all the values that you would find on the reactant side. So if you had a reaction such as H2 plus O2 makes a little H2O, we'll go with liquid. Do a 2 there, do a 2 there. Technically, what you would do is you would go to this table that can be found usually in most textbooks in the back with all the other sort of thermodynamic values. And what you want to do is basically take the delta H of your products. So you would also need to multiply by the coefficient in the balance equation. What you typically will find in this table is the units are kilojoules per mole is the units that you will find for each of these things. So by multiplying by the number in front, which is technically the moles, right? That takes care of the moles part of it. So you would do 2 times the delta H value you would find for water in the liquid state minus 2 times the value of the delta H for H2 in the gas state plus our other reactant, which would be basically 1 times the delta H of the O2 that you would find there. And whatever you get when you kind of subtract all those guys, if you end up with a negative number, then it would be overall a exothermic reaction. If you end up with a positive number, it is a endothermic reaction. A couple of things that's really important when you look up in this sort of table here is you want to make sure that you look things up in the correct state. So for example, water is a very common one. Water could come obviously in liquid, gas, or solid form. So if you have water in the solid form, you want to make sure you look it up in the solid form versus if you had water in the liquid form. So you don't want to just take maybe the first entry that you see in the table might not be the correct state. So you always want to make sure you find the correct state. Other things like things in their standard states, like H2, O2, things like that, have typically delta H values of 0. So anything in a standard state, uncombined, typically will have a delta H value when you look it up in the table of 0. So really our guy on the right here would 0 out. The guy on the left is like 286 kilojoules, give or take 1 or 2 kilojoules. So we would have an overall sort of guy here of basically 2 times that number. There also, some will be negative values, some will be positive values when you look up in that table. So that is a very common way that we calculate the delta H for a reaction. And again, it is sort of our final state minus our initial state, which again is basically our idea of state function there. Any questions on that there? All right. So that's what we see here. Again, if we basically looked up for our products here, all these guys, and then subtracted it from our guys here, So again, if you were going to go to that table to calculate the delta H for this reaction, we would take the products, which is our CO2. So there's only one times the delta H for the CO2 in the gas phase that you would obviously look up, plus 2 times, again, our delta H in the liquid state for water. And that would take care of all the delta H's for our products. We would then subtract it for the 1 times the delta H for our CH4, plus the 2 times the delta H for our O2 that you would look up there. And again, in this case, you can see, we'll steal the number there. You get something like minus 890.4 kilojoules in this process. This is a combustion reaction. It is basically the reaction that happens when you light your Bunsen burner, which we know obviously gives off heat and energy right to the surroundings. And really the number not important for that determination. It is really, again, just the sign that you would see there that is negative. Yes. No, ideally, if you kind of did all those numbers and you looked them up, that's kind of the value, or very close to that value, is what you would get as the result of doing that. Yeah. Yeah, it would be in a big thermodynamic table. I'm not sure where that slide went, but I'll try to find it eventually. But it's just a big table that you can find in the back of the book. And again, it has, usually it's a table that has all the thermodynamic values together. And that's like delta H, delta S, and delta G. These two we will talk about in chapter 16 when we go back, or 17, whatever number it is. This is the one that we see in this particular chapter. So usually it's a big table in the back of the book, and it has all these guys listed, and then all the different sort of guys in their different states, and you can find that. Same thing here for our water. We would take our products minus our reactants. This is actually a phase change that's occurring here. Obviously, we're starting with ice going to liquid water. That obviously is going to be an endothermic process. This number right here, as you may know, is actually what is known as the heat of fusion. Yeah. The heat of fusion for water is 6.01 kilojoules per mole. That is the energy required to change the phase of a substance. When a substance changes from solid to liquid, or liquid back to solid, right? Does that occur at the same or different temperatures? It actually occurs at the same temperature. So for something like water, which is this guy over here, it's basically 0 degrees Celsius is where we get that transition of solid to liquid, or liquid back to solid. That is obviously melting or freezing, depending on which way you're going. And it takes that amount of energy not to change the temperature, but just to simply change the phase of that substance. At 0 degrees, at the normal melting point and freezing point, you basically have both phases in equilibrium with each other. So you have like ice crystals, if we're talking about water. So you got some solid, you got some liquid. It's really not until you get above 0 degrees Celsius that you truly get into true liquid water. And it's not really until you're a little below 0 degrees Celsius that you truly get into like ice and solid form of water. That's also the same thing that happens at the boiling point, right? The boiling point for water is 100 degrees Celsius. That's the transition between liquid and gas, and also going the other way is where condensation occurs, right? Going from gas back to liquid. That also occurs for water, specifically at 100 degrees Celsius, liquid to gas and gas back to liquid. There is energy associated with that transition. That is what is known as the heat of vaporization. And that basically is a delta H value. Delta H vaporization. This is delta H of fusion, sometimes referred to. Same thing, it's the energy required to simply take that liquid water at 100 degrees Celsius to steam, basically, or gas at 100 degrees Celsius, not changing the temperature. So that is, if you ever remember maybe a heating and cooling curve, which we might see here in this chapter. There's like these spots where basically it plateaus out at the temperatures. 0 degrees Celsius, 100 degrees Celsius. That is the transition up here between liquid to gas, and this is the transition down here between solid to liquid. It occurs basically at the same temperature. The only difference is the actual sign that you see in terms of the energy. So for example, for the heat of fusion, if I am going from solid to liquid, is that endothermic or exothermic? Solid to liquid is endothermic. That's put energy in, which means it would require plus 6.01 kilojoules per mole, really. If I go from liquid to solid, that is exothermic. The only difference is negative 6.01 kilojoules per mole. So when we do use anything about like heat of fusion, heat of vaporization, the number's the same no matter which way you're going, but the sign is different depending on whether the process is exothermic or endothermic. Any questions on that there? All right, so another sort of important aspect of, sort of delta H, and another way that we can sometimes calculate the delta H or figure out the delta H for a reaction is by actually looking at an equation where you're actually given a delta H value. So for example, in this equation here, that is like propane, I think, with some oxygen there, cooking some dinner. They have a delta H reaction here of minus 2221 kilojoules. First off, just looking at this, we do know that this is a exothermic reaction, which we would expect since it is a combustion reaction, should give off heat and energy. So we want to calculate the delta H when 0.113 moles of propane is burned with excess oxygen at constant temperature. We could actually apply, and this is sometimes referred to as thermochemical equations here. We could basically apply like a stoichiometry approach to energy. And if you remember stoichiometry, I hope so, is a mole to mole relationship, right? And that's basically based on the coefficients that we see in the balanced equation. And we could do that with the energy component if we actually have it in an equation. And what I mean by that is we could come up with several relationships here. We could say, for example, for every 1 mole of propane that we toss into this equation, we get out minus 2221 kilojoules of energy. And we basically could use it as a conversion factor. If we do O2, we could say for every 5 moles of O2, we get out minus 2221 kilojoules. And we could even do it on the other side, obviously, for every 3 moles of CO2, we also get out minus 2221 kilojoules. And for every 4 moles of water that's produced, we get out that exact same number. So in a question like this, we want to calculate the energy when 0.113 moles of propane is used. In the reaction, this number is for how many moles? It is actually for 1 mole propane. So we could actually do that conversion by taking 0.113 moles of propane. We could use, obviously, our relationship with propane that we get from the equation, or we just use it as a conversion factor. We could say for every 1 mole of propane, we get out minus 2221 kilojoules. The moles of propane will cancel here. So it's very much like a stoichiometry little problem, except that we're kind of inserting energy. And in this case, we end up with, if I hit all the right numbers there, we'll go with about 251 kilojoules, which would be negative, right? So 1 mole gets us about 2,200 kilojoules of energy being released. About 1/10 of that, right? We got about 1/10 of the energy that's going to be released from that, and we would have minus 251. So this is another way that we commonly will use delta H values in an equation to help us determine things. Any questions on that calculation there? Now we could also, before we get there, We can also look at an equation and adjust the equation and the delta H. So sometimes we do need to manipulate equations to get things correctly. So for example, that was our C3H8, right? How many oxygens was it? That was 5, right? And CO2s, there were 3, and water 4, and it was minus 2221 kilojoules, right? All right, thank you. So let's just say, for example, you know, we didn't need 1, but we had like 2. We could simply multiply this entire thing by 2, and that would give us 2 propanes plus 10 oxygens, give us 6 CO2s plus 8 waters. What that does to the delta H value is you would also multiply it by 2. So unlike K values, where we kind of do like squaring and stuff like that, here we actually just multiply by it. And that would get you obviously some 4s there. So minus 4,442 kilojoules, which does make sense. We basically just double the amount of propane and we get twice the amount of energy that comes off. That also means that, for example, if you had an equation like the bottom one and you only needed 1 propane, you could go back through and divide everybody by 2, right? Which will take you back to our original equation. And what we would do with our delta H, we would divide it by 2, and that would take us back, obviously, to our original delta H value. So a couple ways that sometimes we can manipulate these equations that have delta H's is, again, sometimes you may need to multiply by a common number. And what that does to the delta H is you basically just multiply the delta H value by that common number. You may need to divide by a common number, and the same thing there. You can divide the delta H value by that common number. So it does work very different than like equilibrium when we multiply and divide and stuff like that. So there's some differences there. Any questions on that there? Okay. Now, another important sort of thing that we do calculate with heat and energy is what is known as specific heat. Specific heat is the specific heat capacity. It's the amount of energy that's required to change the temperature of 1 gram of a substance by 1 degree Celsius. That is pretty much identical to the definition of calories, except that it's 1 gram of water by 1 degree Celsius, but it's a very similar thing. There is a specific heat equation. I personally roll with this one, which is Q is equal to ms delta T. Q is heat, or energy. So Q is heat or energy. It typically has units of joules or calories. That's lowercase c. M is mass, which usually has units of grams. S is the specific heat capacity, which has units of either joules per gram per degree Celsius or calories per gram per degree Celsius. Again, most people go with joules, but calories are used a lot. That is basically the definition of specific heat capacity. The amount of energy, which is the top number there, joules. You need to raise 1 gram of a substance, which is the bottom there, by 1 degree Celsius, which is the other bottom guy there. That's basically your definition of specific heat capacity. Delta T is the change in temperature, and it should always be what it says there. You should always do the final temperature minus the initial temperature. It is really the temperature change that determines whether or not you end up with an exothermic process or an endothermic process. And as I mentioned earlier, if you calculate Q here and it is negative, we are talking exothermic. And if you calculate Q here and it is a positive number, it is an endothermic process. Since M is mass, that's a positive number. Specific heat capacities are positive numbers. So the only place you could get a negative number is in the temperature change. So you just don't want to take the difference, which in an earlier class, you might have been taught that in like an introductory class. Just take the difference. It doesn't matter. It does matter in our context here. So either you get the negative or you don't get the negative. Obviously, the only way we can get a negative is our final temperature being lower than our initial temperature. And that will only result from somebody losing energy, right? When things lose energy, their temperature comes down. So that is an exothermic type process, which is why we end up with a negative. Opposite to that, endothermic is positive. And the only way for the temperature to become positive, or Q to become positive, is final temperature needs to be higher than the initial temperature. And that is because it's gaining energy. And when it gains energy, temperature reflects that as going up in that process. Also, probably the one place in chemistry where you don't actually need to change it to Kelvin. Yeah, so you can leave the temperature in Celsius. I'll put a note on that. I would say I haven't ever seen a chemistry textbook where they give the specific heat capacity in Kelvin. It's usually in Celsius. I will say physics sometimes give it to you in Kelvin, I think. Yeah, so if you're in physics, you might want to be careful on the temperature, but usually in chemistry books, they will give you the specific heat capacity in degrees Celsius. But again, I know in physics it sometimes does. A couple important values is the specific heat capacity of water. And by the way, this is not negative, it's just from PowerPoint. So it is actually just 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. That is basically also the important conversion here of 1 calorie is our 4.184 joules per gram per degree Celsius. If you have a really high, or if you have a large value for specific heat capacity, does it take more or less energy to change the temperature of it by like 1 degree? It does take more, right? If you have a really low value for specific heat capacity, it takes a lot less energy to change the temperature. That is why people freak out, right? Because water has a very high specific heat capacity, and people get upset when the temperature of the water goes up by like a half a degree, right? Of the ocean, people will go, well, it's just a half a degree, but it's a lot of water, and it takes a lot of energy to make that thing go up by like a half a degree or a degree Celsius. And that's why, people go, hey, it's kind of important that the temperature of the water is increasing, because it takes a lot of energy just to move water, that much in terms of their temperature. Any questions on that so far? Yeah. I would say it would be provided to you. I would say this number here is probably one you should know. It's just one that you use a lot. So just by using it a lot, you'll probably know it, but it will still be provided for you. Specific heat capacity is also really important when you go to the table to also make sure of the state of it as well. Now that's the specific heat capacity, just so we're clear, for liquid water. Yeah. Specific heat capacity for steam or ice, which is obviously water in the solid phase or the gas phase, is about 2 joules per gram per degree Celsius. So it is different. So just like the other table we were talking about, you always want to make sure that when you go to any of those type of tables, that you actually are finding the substance, the correct substance first, but also in the correct state that you need it in, so that you get the correct values. But to answer your question, it probably would be sort of provided to you. So as you can see here, as I just mentioned, if we're talking about ice, we're actually at 2.03, and we're talking about steam, it's 2. Here's some metals. So same idea, if you're heating, iron versus maybe copper or silver or something like that, it'd take a different amount of heat just to get that temperature up by 1. All right. So let's take a look at an example. Why don't you take a second or two and see what you come up with. Determine the amount of energy as heat that is required to raise the temperature of 10 gram sample of aluminum, specific heat capacity 0.89, from 25 to 58. Answer in joules and calories. Okay, so looking at this one, obviously we're dealing with specific heat capacity, so we want to think about our equation, MS delta T. By the way, some books, some people will not use S, some people will use C for specific heat capacity. Some people use SH for specific heat capacity, so you may see some various sort of symbols in there. In this case, we obviously have the mass, which is 10 grams. We also have the specific heat capacity given to us, which is 0.89 joules per gram per degree Celsius. So again, because this is obviously in Celsius, as we talked about, you don't need to convert it to Kelvin. Our final temperature is 58 degrees Celsius, and our initial temperature there is 25. So really, we actually have everybody on this side here, so we just need to plug it in. So that's going to be Q is equal to 10 grams times our specific heat capacity, which is 0.89 joules per gram per degree Celsius. Again, here we want to make sure we do final minus initial, so that's going to be 58 minus the 25 degrees Celsius. In terms of units, the degrees Celsius will cancel, the grams will cancel. That's going to leave just joules left, which is good since that is the unit of energy. That's going to be 10 times 0.89 times our 58 minus 25. And it looks like a 293.7 joules, or if we want to clean it up, maybe to like 290 joules, if we still care about significant figures at this point in our life, which we should, I suppose. We got like 2, 2, and 3 there on the multiplication. This is endothermic or exothermic? This is a endothermic one, as we ended up with a positive value for Q. And that is when we do sort of specific heat at constant pressure, Q actually equals the delta H value when you do a reaction like this. So if you're at constant pressure, the heat that you calculate is actually the same thing as the delta H in this particular case. Any questions on that calculation there? Okay. What's that? Oh, I'm sorry. Thank you. Yeah, so 290 joules. I always miss that part of the question. I don't know why. But we would then take, obviously, there's 4.184 joules in a calorie, right? So we're going to actually divide by the 4.184. So if you use the rounded number of 290, you will end up with like 69, it looks like. 69 calories. Obviously, if you didn't use the rounded number, you might get a slightly different value there. You get about 70-ish there as well. Thank you. Any questions on that calculation there? Why did I round to 290? Just math-wise, significant figures, this has 3 sig figs, right? This guy has 2. When we subtract here, I don't know, whatever we get there, 33 has 2 sig figs. So we're multiplying everything, right? So the lowest number would be 2. In that case, yeah. Other questions? Okay, let's take a look maybe at another one here. 294 joules of heat is transferred to 10 grams of a sample of silver at 25 degrees Celsius. What is the final temperature of the silver? Also in degrees Celsius would be good. Specific heat of silver is 0.24. So see what you come up with. I was going to say sig figs, but our specific heat is what I'm trying to spit out there. All right, so that is our Q is equal to MS delta T. In this case, the 294 is Q. Remember that Q has just 1 unit, joules or calories usually. The specific heat capacity has the 3 units. We also have obviously the mass here, which is 10. We have our initial temperature, which looks like a 25. We're looking for our final temperature here, and we have our specific heat capacity, which is 0.24 joules per gram per degree Celsius. So really, in this case, if we wanted to, we could just solve for the change in temperature, which would be Q divided by MS, right? Again, basically just dividing this to that side to do that. And if we put in our numbers here, we got a 294 joules, I think. We got a 10 grams, and for our specific heat there, 0.24 joules per gram per degree Celsius. Joules will cancel, grams will cancel. When we do the division, the degree Celsius comes to the top. And that gives us a 294 divided by 10 and divided by a 0.24. Gets you like a 122.5 degrees Celsius, which again would be our change in temperature. Sig fig wise, if we wanted to sig fig it up at this point, probably like a $1.20 would be right here with 3, 3, and 2 on the dividing here. Yeah. But remember that this is not obviously our final answers or our final temperature. This is again the change in temperature. And that is where the relationship of the change in temperature is important. The change in temperature being our final temperature minus our initial. So if we use our nicely sig fig number there, that's a 120. Final temperature is what we're looking for minus our initial, which is 25. That means you actually need to add it to this side. And maybe a 145 there degrees Celsius would be our final temperature. Obviously, if you didn't, you would end up with like a 147-ish, I guess. Yes. The last thing we did, as I dropped that, the last thing we did was add, right? So we look at decimal places. So that's a whole number to a whole number. And that's why we end up with something like that. Yes.